So today we will discuss monotone classes. So let's fix a set omega of points, and we will say that a class M, so this is a definition, a class M of subsets of omega will be called a monotone class if it's closed by monotone sequences of sets, which means that if it fulfills two properties. First, I will require that if we have a sequence of sets Aj in M, Aj increasing to A, so remember that by that I mean that the sequence it's increasing and that its union it's equal to A. So if I have such a sequence, then A belongs to M. And similarly, if I have a sequence of sets in M, but now decreasing to a set A, and here again I mean that the sequence is decreasing, so Aj contains Aj plus 1, and the intersection of Aj it's equal to A. Then, if I have such a sequence, I will require that A belongs to M. So a family of subsets of omega M which fulfills these two requirements will be called a monotone class. Of course, an observation. Well, first observation is that if F is a sigma field, then it's a monotone class. And a second observation, which is also very simple, is that, well, if I have a family M alpha of subsets of some set omega, alpha belonging to some index set I, not specified, then if I take the intersection for alpha in I of M alpha, so if M alpha are all monotone classes, the intersection of M alpha for alpha in I is also a monotone class. And this is very easy to prove. To show, let me call this set M. To show that M it's a monotone class, we need to prove that M fulfill the two requirements of a monotone class. So let's consider, say, a sequence of sets Aj in M, Aj increasing to a set A. Since Aj belongs to M, it belongs to each of these sets M alpha. Since M alpha it's a monotone class and Aj it's increasing to A belongs to M alpha. Since this is true for any alpha, A also belongs to M. And the same reasoning for a decreasing sequence shows that the same property holds if the sequence Aj decreases to A. So this is a very simple observation, and it follows, as we did for algebras and sigma algebras, that once we prove this result, we can introduce the notion of the smallest monotone class which contains some class of sets. So let's say that C it's a class of subsets of omega. Now we we'll represent by M of C the smallest monotone class which contains the class C. And this can be obtained just by taking the intersection of all monotone classes which contain C. So let me call M alpha all the monotone classes which contain C. This family is clearly not empty because P of lambda, all the subsets of lambda, forms clearly a monotone class. So this family of monotone class is not empty. By taking its intersection, by the previous observation, we obtain a monotone class. And this monotone class is the smallest one, because any monotone class which contains C, it's somewhere here, and therefore contains the intersection. So we will represent by me M of C the smallest monotone class, which will be called the monotone class generated by the class C. So now let me state the main theorem of this lecture. So let's A be an algebra of subsets of some set omega, so A contained in P of omega. And remember that we represent by F of A the sigma algebra generated by the algebra A, by M of A the monotone class generated by A. And what I claim is that these two classes are in fact equal, and this result will be extremely important, used many times. So it's very important to remember it, because it will be used in these lectures a certain number of times. So let me present a proof of this result. There is one relation which is extremely simple. We know that a sigma algebra is a monotone class, so F of A is a monotone class. We've seen that. It was my first observation. Certainly F of A contains A, because it's the smallest sigma algebra which contains A, so it contains A. So F of A, it's a monotone class which contains the algebra A. Therefore, by definition, F of A also contains M of A. So the fact that the monotone class generated by the algebra A is contained in the sigma algebra generated by the algebra A, it's elementary and has been proved in 2 lines. So the difficult part in this proof is to show that the sigma algebra generated by A is contained in the monotone class generated by A. We have to show that F of A is contained in M of A. So we will prove that in 2 steps, showing that M of A contains the algebra, but that we know already, because M of A is the monotone class generated by the algebra, and therefore it contains the algebra. But we will show, and this is the main point, that M of A is a sigma algebra. And in order to prove that M of A is a sigma algebra, we will first show that M of A is in fact an algebra. So this is the main step in the proof, is to show that M of A is an algebra. And in order to do that, we will introduce class of sets. So let's take E in MA. I will represent by G of E these sets F in M of A, such that E minus F, E intersection F, and F minus E, they all belong to M of A. Right? So for a fixed set E in MA, I will represent by G of E all the sets F in MA for which E minus F, E intersection F, and F minus E belong to MA. And my claim, my first claim, is that assume that E belongs to the algebra, then G of E will be a monotone class which contains the algebra and therefore contains the monotone class generated by A. So, as I said, so my claim is that if you take a set E in the algebra, then G of E contains the monotone class generated by A. To prove that G of E contains this monotone class, I have to show two properties. First, that G of E contains the algebra, and that G of E is a monotone class. So let's prove these two properties. I will start with the first one. I want to show that A is contained in G of E. Remember that I'm assuming that E belongs to the algebra. Well, to prove that, I have to take a set A in the algebra and show that it belongs to G of E. To prove that it belongs to G of E, I have to show that these three properties hold for H. So I have to show that E minus H, E intersection H, and H minus E belong to M of A. Well, but since H it's an element of the algebra and E it's an element of the algebra, these three sets, they all belong to the algebra, and the algebra is contained in the monotone class generated by the algebra. Therefore, they all belong to the monotone class generated by the algebra, and therefore H belongs indeed to G of A. And this proves that the algebra is indeed contained in G, the set G of A, which I defined. Now we have to prove that G is a monotone class, and that's also very easy. Assume that I have a sequence H, K increasing to H, and that H of K belongs to G of E. Remember that this means that H of K it's an increasing sequence whose union is equal to H. Well, since HK belongs to G of E, this means, for instance, that E minus HK belongs to M of A. But since HK is increasing to H, this means that E minus HK is decreasing to E minus H. Since M of A is a monotone classes, we have here a sequence of sets in the monotone class which is decreasing to a set. Therefore, this set belongs to the monotone class because the monotone class is closed by decreasing sequence. In the same way, we can show that E intersection hk, which belongs to the monotone class because we are assuming that each hk belongs to G of E. Well, since these sets belong to the monotone class and hk it's increasing to H, this sequence increases to E intersection H. Since M of A it's a monotone class and this sequence increases to that sequence, to that set, this set also belongs to MA. And by a similar argument, we can show that HK, H minus E will belong to M of A because HK increases to H. Therefore, HK minus E increases to H minus E. Since M of A is a monotone class, H minus E belongs to M of A. Therefore, we proved that E minus H, E intersection H, and H minus E all belong to the monotone class A, and therefore that G of E it's closed by increasing sequence. A similar argument shows that G of E it's closed by decreasing sequence. You can consider sequence HK decreasing to H, repeat arguments very similar to those which I just presented to conclude that H also belongs to G of E, which proves that G of E it's a monotone class. Once you know that G of E contains the algebra, which I proved, and that G of E it's a monotone class, we just proved this assertion, you conclude from that that G of E also contains the smallest monotone class, which contains the algebra A, which is M of A, which proves that M of A it's indeed contained in G of E as I claimed. So we are proving that the monotone class generated by the algebra contains the sigma-algebra generated by the algebra. And to prove that, we are first showing that M of A is an algebra. Well, what did we do up to now? We introduced these sets. So if E belongs to the monotone class generated by A, we define G of E as the sets F in M of E for which these three sets are in M of A. And we proved that if we take a set E in the algebra, then the monotone class generated by A it's contained in G of E. Now we will show that if I take E in M of A, the same result holds. So I'm extending the first claim to sets in the monotone class. We proved this claim for sets in the algebra. Now I'm claiming that the same relation holds if we take a set E in the monotone class generated by A. So again, to prove this relation, we will show that G of E is a monotone class. And B, that G of E contains the algebra. If G of E is a monotone class which contains the algebra, it contains the monotone class generated by A, which is what we want to prove. So let's prove A and B. The proof of A, it's identical to the proof of A in the case in which E is an element of the algebra, but let's just recall it. So I'm fixing a set E in MA, and I want to show that G of E it's a monotone class. So let's consider sequence HK in G of E, and let's first assume that HK increases to H, and we want to prove that H belongs to G of E. Well, but since hk belongs to g of e, so let's recall the definition. We know that e minus hk is an element of the monotone class. hk, it's increasing to h, therefore e minus hk is decreasing to e minus h. Well, since we have a sequence of sets in the monotone class which is decreasing to a set by the property of the monotone class, we know that e minus h belongs to M of A. In a similar way, we can show that E intersection H belongs to the monotone class, as well as H minus E belongs to the monotone class. This means that we proved that E minus H, E intersection H, and H minus E are all in the monotone class, and therefore they belong, H belongs to G of E. So we just proved that if we have a sequence hk in G of E, hk increasing to H, we just proved that H belongs to G of A, G of E. Right? Note that we know that H it's an element of M of E because we know that hk it's an element of G of E. Therefore, H of k it's an element of the monotone class. Sorry, here there is a mistake. It's not M of E but M of A. So just observe the following. I'm claiming that H belongs to M of A, and this is clear because hk belongs to G of E. So hk belongs to G of E, which means that hk also belongs to M of A, and hk it's increasing to H. Since M of A it's a monotone class, H belongs to M of A. So we prove these three properties. We also know that H it's in M of A, and therefore H belongs to G of E. So this proves that if you take any increasing sets, increasing to a set, it belongs to G of E, which shows that G of E it's closed by increasing sequence, and the same argument holds for decreasing sequences. This proves that G of E it's indeed a monotone class, as we claimed. So we proved this first assertion, that G of E it's a monotone class. Now I will show that G of E contains the algebra. So I want to show that any element of the algebra it's contained in G of E. So let's take H in the algebra, and we want to show that H it's contained in G of E. Well, since H it's an element of the algebra, it's also an element of the monotone class. So to prove that H belongs to G of E, we have to show that E minus H, E intersection H, and H minus E all belong to M of A. So we have to prove that E minus H, that E intersection H, and that H minus E, they all belong to M of A. Right? However, we have proved that G of H, because H it's an element of the algebra, by the first part of the proof, we know that G of H contains M of A. Right? In the first part of the proof, we have shown that if we have an element H of the algebra, then G of H contains the monotone class. If G of A contains the monotone class, since E is an element of the monotone class, this means that H minus E, H intersection E, and E minus H they all belong to M of A, right? By definition of the class G of H, since E is an element of M of A, all these three sets belong to M of A. And this is exactly what we need to prove. Okay? So the second statement, the statement that the algebra is contained in G of E, follows in fact from the first part of the proof. Follows from the fact that for any element of the algebra we have that M of A is contained in G of E. So this proved claim B, and as I said, from these two claims we conclude that G of A contains the monotone class generated by A. So up to this point, we proved that for any element E in M of A, G of E contains M of A, where G of E is given by this definition. Now, let's prove that M of A is an algebra. To prove that M of A is an algebra, we have to show first that omega belongs to M of A, but this is clear because M of A contains the algebra and omega belongs to the algebra. Then we have to show that M of A is closed by complement, so we have to show that if E belongs to M of A, then E complement belongs to M of A. But that's very easy because since E belongs to M of A, and we have shown that G of E for any E in A contains, this implies that E belongs to G of omega, right? Omega is an element of the algebra, and M of A is contained in G of omega, so E belongs to G of omega. And since E belongs to G of omega, let's see what this tells us. Well, let me write here what G of omega, just because I'm using E with a different meaning in these two expressions. So G of omega is the sets F in MA, such that, well, E is omega, so this is omega minus F, which means F complement, omega intersection F, which is F, and omega minus, F minus omega, which is the empty set. They all belong to M of A. So this is what is G of omega. So that since E belongs to G of omega, E complement belongs to M of A, and this is exactly what we want to show, right? So since G of omega contains M of A, E belongs to G of omega, and by definition of G of omega, we obtain that E complement belongs to M of A. So M of A is indeed closed by complement. And finally, we have to show that M of A is closed by finite intersections, which means that if I take E and F in M of A, I have to prove that E intersection F belongs to M of A. Right? But since G of E, we proved that G of E, if E belongs to M of A, contains M of A. And F is a set of M of A, therefore F is a set of G of E. And since F belongs to G of E, we have that E intersection F belongs to M of A. Therefore, we proved that M of A is indeed closed by intersections. And this proves that M of A is an algebra. So now that we proved this claim, it's very easy to conclude that M of A is indeed a sigma algebra. So now we finally claim that M of A is a sigma algebra. Right? To prove, well, we proved that it's an algebra, so that to show that it's a sigma algebra, we have to show that M of A is closed by countable union. So let's consider a sequence AJ and M of A. Well, since M of A it's an algebra, we want, so to prove that it's closed by a sigma, it's closed by countable unions, what we have to show is that the union of AJ belongs to M of A. So this is what we need to prove. Well, but since M of A is an algebra, we know that the union from 1 up to n of AJ it's an element of M of A. And now, since M of A it's a monotone class, and this sequence, the union from 1 to n of AJ, increases as n goes to infinity to the union for j greater or equal than 1 of A of j. So from the fact that M it's a monotone class and that these sets belong to M of A, we conclude that the countable union is also an element of M of A, and therefore that M of A is closed by countable unions, and therefore it's a sigma algebra. So this proves that M of A is a sigma algebra. We have shown that we know that M of A contains A. It's the smallest monotone class which contains A, therefore it contains A. And from these two properties, we conclude that it also contains the smallest sigma algebra which contains A, which is the sigma algebra generated by A. And this is exactly what we wanted to prove. Therefore, this concludes the proof of this theorem.